Yes, good morning, girls. Today we are going to discuss about properties of a binary tree. So already we have seen the definition of binary tree, why it is called a binary tree. So a tree is called a binary tree whether it is when it is empty, a empty tree, or it has minimum or maximum of two children. So one left child and one right child, and each of it is itself is a binary tree. So this is how your binary tree looks like you can remember, like the children of the root, or the children which are there in that particular tree, will not have more than two children. So will not give rise to more than two children. Any root cannot give rise to more than two children. It can be less than two, or it can be uh, I mean, null without children, or it can be less than 2 or equal to 2 but not more than 2. So this is about your this is the definition of your binary tree, right? So we will see what are the properties of this binary tree. So what is a tree? Generally, we have seen that a tree is a connected acyclic graph. A tree is nothing but a graph which doesn't have any cycles. Acyclic in the sense no cycles. If it has cycles, then automatically it becomes a graph. So it will not have any cycles. So such a graph is called a tree, right? Next, a tree is the simplest non-trivial type of graph. It has several properties that there exists a unique path between any two vertices. Yes, there exists one and only one path between any two vertices, because if more than one path exists between any two vertices, then what happens? Automatically it forms a circuit, and it contradicts with the definition of the binary tree. So these are the three main important properties with respect to a tree. So if let's take T as a tree, let's treat T as a tree, then we will see the how these three properties are, satisfying the conditions for a binary tree. So the first one is there exists a unique path between every two vertices. Yes, there exists a unique path between every two vertices. So between any two vertices, between any two nodes in the tree, there exists a one and only one path. If there is more than one path, then automatically it is not treated as a tree, it becomes a graph. So there exists only one path between any two nodes or vertices, right? Next, the number of vertices is one more than the number of edges in the tree. So we will see how this property holds true for the tree. And the third one is a tree with two or more vertices has at least two leaves. So when a tree has two or more, minimum two and more than that vertices, it will have at least two leaves. So it is the minimum number of leaves it can have. It can have more than that leaves, more number of leaves also, right? So let's see these properties, that how we prove them, how these hold true, right? The first one is the property one comes from the definition of tree. Yes, the definition itself says that a tree is a connected graph. Exists at least one path between any two vertices, right? So if there are two or more paths between a pair of vertices, then it forms a circuit. What it forms? It forms a circuit. So it is no longer a tree, it is a graph then. So in order to become it to a tree, whether it is a binary tree or complete tree, full tree, skewed tree, whatever you call, in order to become a tree, there should exist only one and only one path between any two vertices of a tree, right? Now the second one is property 2. What does property 2 say? It says that the number of vertices is one more than the number of edges in the tree. So the total number of edges in the tree is always plus 1, the number of vertices is always plus 1 than the number of edges in the tree. So V is equal to E plus 1, right? So V is equal to E plus 1. This is what you have to remember. Let's keep that in mind and we will see how it holds true. Right? See, let's say consider a tree T with a total number of edges E and total number of vertices V. So the number of edges is E and the number of vertices is V. So for what we are taking here is first step, a tree with one vertex contains no edge and a tree with two vertices has one edge. See, if there is only one and only one vertex in a tree, it is also called a tree, but there exists no edge. Where it will go, where comes the edge between with only one vertex? When you have two vertices, then you can draw an edge between those two vertices. When there is only one vertex, how can you draw an edge? Which isn't possible. So a tree with one vertex contains no edge and a tree with two vertices has one edge. So if a tree is having two vertices, then automatically there exists an edge between those two vertices. If those two vertices are not connected by an edge, then they are called isolated trees, right? So that doesn't form a tree if they are not connected, right? So with this step we will try to prove this number of edges is number of vertices is plus 1 than the number of edges. See, let us consider that there is an edge AB in T such that the removal of the edge AB divides T into two disjoint trees T1 and T2. See, this is the tree we are considering. So we are taking this as edge A. So this is the whole tree T. So if you remove this edge between these two vertices 1 and 2, then this will be an independent tree and this will be another independent tree, right? So T1 and T2, and this is the edge between these two vertices A, B. So you name them as A and B. So with the removal of one edge between these two edges, these two vertices, edge A and B, the edge joining A and B, it gives rise to two disjoint trees T1 and T2. So T1 and T2 are created here, and you remove this edge between these two vertices. So where T1 contains the vertex A and all the vertices whose paths to A in T do not contain the edge B. So automatically, so if you take this as A and this as B, so this tree will contain all the vertices which are connected to A and which do not contain B, because B is in the other tree, right? So how come you will have edges which connect it to A, and this tree doesn't contain B, so there are no edges mapping from B to A. There is only one edge and we have removed that. Next, see, and T2 contains the vertex B and all the vertices whose paths to B do not contain the edge AB. So here also it will contain all the edges which do not contain A and B. A and B we have removed. There is no chance of an edge between A and B. So this tree doesn't contain any edge between A. It does not include an edge which exists between A and B. So from this we are taking the hypothesis that T1 and T2 have how many vertices? V minus 1 vertices, right? So see, we have removed one, what you say, edge. So it is giving rise to V minus 1 vertices, right? So see, since both T1 and T2 have at most V minus 1 vertices, we are concluding that E1 is equal to V1 minus 1, E2 is equal to V2 minus 1. So the number of edges is equal to our number of vertices minus 1. So the reverse of your actual statement here. Number of vertices is 1 more than the number of edges. So V is equal to E plus 1, E is equal to E minus 1. So we are taking the hypothesis from there. So both trees have how many vertices? V minus 1 vertices, right? So where E1 and E2 are the number of edges and V1 and V2 are the number of vertices in T1 and T2 respectively. So if you add these two equations, e1 plus e2 is equal to v1 plus v2 minus 2, right? So E is equal to, so the total number of edges is equal to e1 plus e2 plus 1. Yes, how we have taken this? If we try to count all the edges, then we have to connect this edge also. Then there comes E is equal to e1 plus e2 plus 1, and v is equal to total number of vertices v1 plus v2. So here we give rise to this. If you substitute this E with, see, if you substitute here this in this equation with this e1 plus e2 plus 1, E is equal to, and v1 plus v2 is equal to v, then this minus 1 comes to this side and it becomes plus 1. So we have E is equal to v minus 1. So a little mathematical calculation which you can do on your own. So this is how the property holds true, that the number of vertices is one more than the number of edges in the tree. So always the number of vertices is plus 1 the number of edges in the tree. Excuse me. Next, what is the property 3? Property 3 is a tree with 2 or more vertices has at least 2 leaves. So when a tree is having 2 or more vertices, it will have at least 2 leaves. So how it is, how we prove this is, it is generally an extension of property 2. So the sum of degrees of the vertices in any graph is equal to 2e. So then what is degree? Again, you have to define the definition of what a degree is. A degree is nothing but the inward and outward edges of a particular node or vertex. If it is a directed tree, you will only count the inward edges. Sorry, if it is a directed tree, you have to count the inward and outward edges. If it is not an undirected tree, you will count the edge only once. So the number of degrees of the vertices in any graph is equal to 2e. So when you calculate the total number of vertices, the degrees of the total number of vertices in the graph, then it is 2e. So what is e? E is equal to v minus 1, right? So you are multiplying it with 2, so 2 into v minus 2, 2v minus 2. So since a tree with more than one vertex cannot have any isolated vertex, there must be at least 2 vertices of in degree 1 in the tree. So when there are 2 vertices, then automatically those 2 vertices have to be joined. There shouldn't exist an isolated vertex. If you don't join them, they are called isolated vertices, right? So a tree with more than one vertex cannot have any isolated vertex. There must be at least 2 vertices of in degree 1 in the tree. So there must be at least 2 vertices of in degree 1 in the tree, right? So other properties. So what are the other properties that we are trying to prove here? Next, the maximum number of nodes of level I in a binary tree is 2 power I minus 1, where I is greater than or equal to 1. So if the number of nodes, the maximum number of nodes at a particular level in a binary tree, if you want to calculate, then you are using this equation like 2 power I minus 1. So you will calculate the number of edges by using this expression 2 power I minus 1, where I is greater than or equal to 1. And how you calculate the number of nodes? Maximum number of nodes at depth d by this calculation, by this expression 2 power d minus 1, where d is d greater than or equal to 1. So how you calculate the level and how you calculate the depth, we have already discussed. So how will you come to know the level? What is the level of a particular node, and how will you calculate the level of the particular node or depth in a tree? So this we have already seen. So let's move on how to prove these two properties. We have only, if you see that we have only one root, okay, one node that is root at level 1. So you are taking this, you are considering that level as 1 of the root of the level of the root is considered as 1, not 0 here. So that is what we have to keep in mind. So see here, so the maximum number of nodes that can exist from that particular node is 2 power I minus 1, and you substitute this I with 1. So 1 minus 1 is 0, so 2 power 0 is 1. So this is true when there exists only a root node at level 1. So by induction hypothesis, we take that I is greater than 1, then the maximum number of nodes on level I minus 1. Okay, so if I is greater than 1, so how to calculate the maximum number of nodes at the level I minus 1? So you're just substituting I with I minus 1, so it is 2 power I minus 2. So it is so the maximum number of nodes at any particular level can be taken as 2 power I minus 1. So if it is greater than I minus 1, then it will be, we will be substituting I with I minus 1, and you can calculate the number of nodes as 2 power I minus 2. And here we are assuming that the level of the root node is considered as level 1. If you consider it as 0, then it should be, the expression should be this 2 power I only, because if you take I minus 1 minus, the whole expression will go wrong, right? So 0 minus 1, 2 power minus 1, so there isn't any meaning for that particular value, right? So so the maximum number of nodes at any particular level is 2 power I minus 1, where I is greater than or equal to 1. Next, since each node in a binary tree has maximum degree 2, the maximum number of nodes at level I is 2 power I minus 1. So the maximum number of nodes at depth D. So how are you taking at depth D? Then it is sigma I is equal to 1 to D and 2 power D minus 1. So you will be calculating the number of nodes at any particular depth D of the binary tree. Then you can do that by using this expression 2 power D minus 1, where D is the depth of the tree. So since each node in a binary tree has maximum degree 2, yes, though in a binary tree there exists only two leaves for any particular node, right? So the maximum number of nodes at level 1 is 2 power I minus 1. So relation between number of leaf nodes and degree 2 nodes. So how can you relate the number of nodes and the degree 2 nodes? Degree 2 nodes in the sense the nodes which are having two edges, two incoming edges, then becomes a node of degree 2, right? So in any non-empty tree, if there are n0 leaf nodes and n2 nodes of degree 2, then n0 is equal to n2 plus 1. n0 is equal to n2 plus 1. So how will you prove this, that if n0 is the number of nodes with 0 leaf, I mean there are no further nodes spanning from it, it doesn't have any leaves, it doesn't have any children, so they are the leaf nodes. And n2 is the nodes with degree 2. So see, how we are trying to prove this is, n1 is the number of nodes with degree 1 and n is the total number of nodes. So we are considering that in a binary tree, at most the number of degree for any particular node is 2. Then we will come to we can calculate the total number of nodes in that particular tree by using this expression n0 plus n1 plus n2. So number of leaf nodes plus number of nodes with degree 1, number of nodes with degree 2, right? If the number of branches is b, then n is equal to b plus 1. B is nothing, a branch is nothing but you can call it as an edge, right? So n is equal to b plus 1. So number of vertices is equal to e plus 1, right? So n is equal to number of nodes is equal to b plus 1. So for a binary tree, all the branches stem out from a node of degree 1 or 2. Yes, this holds true because a binary tree contains at the max 2 children, right? So always stem, all the branches come from a node of degree 1 or 2. So you are writing it as b is equal to n1 plus 2 into n2. So n1 is the number of nodes with 1 degree and n2 is the number of nodes with n2 degree. So n is equal to b plus 1, right? So you are substituting this. So this is n here, actually it is not b. So you are substituting n is equal to, you are replacing it with this equation, b is equal to, okay, n1 plus n2, n1 plus 2 into n2 plus 1, n is equal to, actually this is n is equal to, right? So by subtracting this 7.2 from 7.1, you have this expression, number of leaf nodes is equal to n2 plus 1. So you can do this using your mathematics, right? So I'm not further diving deep into this. So when you subtract this equation, equation from this, you will have this conclusion: number of leaf nodes is equal to number of nodes having degree 2 plus 1. Next, binary tree with n nodes having n plus 1 external nodes. So how you calculate the number of external nodes? If it is having n nodes, it will have n plus 1 external nodes. So taking the base case of a tree that with only one node, that is the root, it has 2 external nodes or nullings. So when there is only one node, that is the root, it will have only it has 2 external nodes or nullings. So if n is equal to 1, the number of external nodes is n plus 1, that is 2. So the two nodes which are coming out of that particular node are called external nodes, right? So if there are n internal nodes, if there are more than, if you are exceeding level 1, if you go to level 2, then there exists internal nodes as well. So level 1 nodes are called as internal nodes and level 2 nodes are called as external nodes. So in this, if there are n internal nodes, where the left subtree has L nodes, okay, so the left subtree is having L nodes, then the right subtree will have n minus L minus 1 internal nodes. One, because we are taking out the root here, because root is taken into the left subtree. So right subtree is, we have to remove, we can't consider root into this tree, so we are taking it as n minus L minus 1, right? Next, by induction hypothesis, the number of external nodes of the left subtree is L plus 1. So the number of external nodes in the left subtree is L plus 1. So when you replace this right subtree, so n minus L minus 1, you replace this L with n minus L minus 1, so it is n minus L. So the number of external nodes in the left subtree will be n minus L. So the total number of external nodes, total number, including the left subtree and the right subtree, is n plus 1. So this is how you can prove that if a binary tree is having n nodes, then it will have n plus 1 external nodes. Okay, so this is about your properties of the binary tree. So in the next class, we will see about binary tree abstract data type. So if you have any doubts, ping me in the group, girls. So these three property as these three property are very much important. So how they are proved, this is what you have to keep in mind. And next, these two, the maximum number of nodes at level 1, level I, and the maximum number of nodes at level D, and how the leaf nodes and degree 2 nodes are calculated, and also how many number of external nodes, internal nodes, external nodes. Internal node means they can give rise to some extra nodes, right? I mean, they are further having leaves. External nodes are nothing but your leaves, right? So this is how you will calculate the number of external nodes for an n nodes. So you have n plus 1 external nodes, right? So these are the properties of a binary tree. So let's discuss about binary tree abstract data type in the next class. You just update your notes, girls. If anyone is writing the notes, please do update your notes till this topic. Take care. Bye.